Hello, classmates and Dr. Isaacs, and thanks so much for watching my presentation on important action areas in urban Los Angeles for increasing albedo and vegetation cover. This presentation will go over background and study area, methods, results, conclusions, and future directions. Now, Los Angeles is known for concrete and smog, but it lies within a biodiversity hotspot of the California floristic province. The last 100 years of urbanization in LA has brought a decrease in biodiversity and an increase in heat. My research aims to look at solutions to both of those issues within my study area. The temperature and duration of heat events are on the rise in Los Angeles, and while climate change plays a role, the urban heat island effect is the greatest contributor to rising temperatures in LA, which is 2 to 10 degrees warmer than surrounding areas. Despite all that heat and pavement, there is opportunity for biodiversity. Within the urban core of LA, there was an incredible study done here at the Natural History Museum in Los Angeles, showing that strategic planting could increase biodiversity within the city. Last summer, I documented some of it for my conservation biology class and saw for myself an array of pollinator diversity. Numerous newer studies are even showing that pollinators like bees can really thrive in urban areas and that cities are even a refuge from natural and agricultural areas because of the lack of pesticides and the increased managed floral resources in cities. Increasing vegetation brings numerous ecosystem services to urban areas as well. It can improve flora and fauna biodiversity, improve air quality, reduce noise, mitigate urban runoff, and improve recreational enjoyment. Lastly, urban vegetation absorbs heat, and trees provide humidity and shade. Planting can improve microclimates by providing urban cooling. My initial research topic was to use what I knew about urban tree and vegetation planting and map out areas in close proximity to the museum to create conservation stepping stones. I looked at vegetation maps like these and higher than average heat severity to pinpoint potential location. I was hoping for a 2-for-1 vegetation special, an increase in pollinator diversity, and cooling down neighborhoods. But my research took me on a different path. I was able to have a really great conversation with entomologist Emily Hartop, who is the lead author of that study. I planned to ask her about foraging ranges so I could create conservation stepping stones, and she said it was less about connectivity and more about simply strategically planting. She explained that if you build it, they will come. Connectivity was less important than simply starting your strategic planting. Using this "if you build it, they will come" model, I had more freedom in where I chose my potential areas for strategic planting. Rather than looking for places within a couple football fields of the Natural History Museum based on foraging ranges of certain pollinators, I could just look for areas in the most need for increased vegetation and urban cooling. Through my ArcGIS explorations and many more scientific papers, I also realized it wasn't just vegetation that was helping, it was albedo. In looking at satellite data for areas of high heat severity, I could clearly see that albedo was decreasing land surface temperatures, like in the bottom right-hand section of this photo. And in a recent paper out this year about cooling Los Angeles down, it was a combo of vegetation and albedo that does the trick. Scientists said that if aggressive action is taken with a combination of reflective surfaces and vegetation increases, 1 in 4 heat-related deaths could be prevented under future climate scenarios. With my new information and a little GIS under my belt, my research question became clear. Where are important action areas to strategically plant and increase albedo? Specifically, I was looking at areas near the Natural History Museum with higher temperatures, low vegetation, low albedo, and high social vulnerability. Let's move on to my methods. In order to identify important areas of action, I divided my study area up by U.S. Census tracts so I could also use census data for analysis. I identified census tracts within a 4-kilometer radius of the Natural History Museum, so potential increases in biodiversity could be compared to data that was already obtained by the museum. I then created a layer in GIS Pro from these selections. To test for areas of low vegetation, I used Landsat data for 2021 obtained from the United States Geological Services website. I applied a normalized difference vegetation index in ArcGIS Pro to identify vigor and density of biomass, and then reclassified it into areas of low, medium, and high vegetation. I used the clarity and precision of Google Earth to compare and contrast the data obtained from NDVI and Landsat 8 to double check for accuracy. Calculating albedo was trickier. With help from Dr. Isaacs, I used an equation posted on the Yale Center for Earth Observation, derived from a series of algorithms that were used to calculate land surface albedo from satellite sensors. I applied the equation to my Landsat 8 data through the raster calculator in order to show the sun's reflectiveness of land cover. You can see in this image areas of high albedo in purple, medium albedo in orange, and low albedo in yellow. Now, in order to determine which communities were most at risk from death or illness from heat severity, I obtained data from the CDC Social Vulnerability Indicator, or SVI. The SVI gives track-level data of communities that are vulnerable to natural disaster in order to help public health experts plan. The SVI is significantly associated with heat-related deaths because of the multiple social factors that are taken into account with ranking communities by socioeconomic status, household composition and disability, minority status and language, and housing type and transportation. Using a binary suitability analysis through the raster calculator, I determined areas of both low vegetation and low albedo. In this map, you can see the Natural History Museum indicated in the blue tab. Areas of medium and high albedo and vegetation are in green, and low vegetation and low albedo in yellow. Final data was added from the PRISM Climate Group, which provides spatial climate datasets for mean temperature, which is calculated using long-term averages and climatologically aided interpolation. To further narrow down a manageable 4 important action areas, I looked at the areas which had extremely high social vulnerability index in the 96th percentile, which means that these were communities that were in the top 4% of social vulnerability and therefore heat vulnerability. My results showed the following 4 census tracts as important action areas for vegetation and albedo increases. Let's zoom in a little on these, which I numbered for future analysis. Let's take a look at potential opportunities in these action areas. Within ArcGIS Pro, I chose coordinates within these tracks at random to take a closer look within Google Earth. And as we zoom in, you can certainly see these are at the urban core of LA. Let's talk a little bit about this track. As you can see, there's plenty of opportunity here to increase vegetation and increase albedo. Many of the streets are dark black, and there's a lot of opportunity to increase albedo on roofs. And as we look down this street, we see a lot of great things happening with those reflective roofs, but not a lot of vegetation on the median strips. But as you look closer here, you can see tiny strips of shadow, which indicates that what's being planted here is the iconic LA palm tree. And unfortunately, this palm tree doesn't provide a lot of shade or cooling. If you compare the palm tree to a larger fig tree on the right side of the screen, you can see the tremendous amount of shade provided by the fig tree and not a lot by the palm tree. So what I would do in this scenario is I would take a look at the roofs, try to change them into a more reflective surface, increase reflective surfaces on the pavement, and intersperse between these palm trees large shade trees and other vegetation. In conclusion, the big picture here is simple. Cities are warm due to the heat island effect and climate change. Increasing albedo can cool these areas down, and when vegetation and albedo is increased, 25% of heat-related deaths in Los Angeles can be prevented. Along with urban cooling, strategic planting of vegetation can encourage biodiversity, improve air quality, decrease noise, and improve communities for the better. Using these important action areas, we can start with the places that need it the most. Now that important action areas have been identified, data collection can begin. My next steps would include the following stages. Stage 1. I would start analyzing ground-level thermal sensors throughout the 4 important action area tracks and 4 control tracks. I'd also set malaise traps to measure microfauna biodiversity in all tracks in the study area. Meanwhile, I'd identify and plant drought and heat-tolerant plantings and identify specific areas for increasing albedo. Stage 2, I'd implement strategic planting and albedo modification, and in Stage 3, I'd monitor and check for temperature decreases and biodiversity increases. I'd then begin implementing along additional important action area tracks. The technology is here, the data is in, and now it's time to take action in these 4 tracks. And I leave you with this updated version of an ancient proverb. The best time to increase reflective surfaces and plant trees was 20 years ago, but the second best time is now. By identifying places within my study area as important action areas, we can get to work putting boots on the ground and then one foot in front of the other. Thank you for watching.